So you're back for more. This is the second installment in what's typically Chapter 4 of an AP College textbook, and this session is going to focus on chemical equations. It's pretty vital to your success on the AP exam, so it's a good thing that you're here. Chemical equations transform elements and compounds into new substances by making and breaking bonds. And it takes energy to break a bond, but when a bond is made, energy is released. But that will be another unit called thermodynamics. So in this unit, no energy or time is alluded to. We'll deal with time in another unit called kinetics. So much to look forward to. But this is the building block of your understanding here. So make sure this building block is nice and big and strong. Antoine Lavoisier is the gentleman. That was my best attempt at a French name pronunciation with my Texas accent. But he's the gentleman that actually stated the law of conservation of matter, which states matter can neither be created nor destroyed. Never get into a debate about that with a particle physicist, because that is debatable on that level. But for a chemistry level, it's still a good law. And so this means that balancing equations is all his fault. We have to have an accounting mechanism for keeping up with all of that matter. If it cannot, it just disappear. So not all reactions are going to fall neatly into just one category. You learned some categories in first year: decomposition, composition, single replacement, double replacement, neutralization. There's way more categories than what we taught you in first year. But we got to start somewhere. So we're going to be starting with AP net ionic equations very soon, where you're going to see several more additional categories involved. But our first category that we're going to discuss today is about precipitation reactions. A lot of points are tied to precipitation reactions across this exam. So this is a skill that you want to master early, and you want to use it often. So the formation of a precipitate is a driving force for a chemical reaction. A precipitate is defined as an insoluble solid that is formed when two aqueous solutions are mixed. So essentially you have two clear solutions. They can be colored, they can be colorless, but they're definitely clear and you don't see any solid stuff floating around in them. But when you mix those together, then you get a precipitate. And that precipitate is a solid. So we often separate the precipitate by using filtration. So we can either use gravimetric filtration, where you don't use any special equipment other than a funnel and a piece of filter paper that's folded up to make like a paper cup to capture the solid. And you just let gravity prevail, and drippy, 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 the filtrate drips right on through that filter paper and leaving the solid captured on the paper, which we then carefully take out and lay out flat so that it can dry faster, and we dry it and we mass it and we do our stoichiometry with it. Excuse me. So sorry. Then the other way to speed up this process is to use a suction or vacuum filtration. You may have done this in laboratory if you've ever hooked up a Erlenmeyer flask that has a little glass sidearm spout on the side of it to a rubber hose, and then to another gizmo called an aspirator that is often attached to your sink. And you just let the water run, and that running water will actually create a vacuum that's going to make the dripping go a lot faster. So you can filter this out much, much faster with a little bit fancier equipment. But in order to identify the identity of the precipitate, you have to know your solubility rules. And you really need to expect to be quizzed on these regularly. We're going to start, like I say, net ionic equations soon, where you're going to go down in flames if you don't know these rules. And I'll just tell you that there are as many different sets of these rules as there are chemistry authors. So most alkali metals, those would be the 1A metals on the periodic table, the sodium family, and ammonium ion salts are soluble. So if you see ammonium anything or the 1As with anything, then you know good and well that you have something that's soluble. So if you've ever seen those t-shirts that say rule number 1, the mother is always right, and rule number 2, if the mother's ever wrong, consult rule number 1, because the mother's always right. This rule number 1 is in bold because it takes priority. So no matter what I say from this point forward, if you've got sodium, potassium, any of those alkali metals involved, and then ammonium salts, these things are soluble. So chloride, bromide, iodide compounds are soluble except for silver, mercury, and lead. Now silver, mercury, and lead show up in a couple of different rules, and so I've lovingly dubbed them the heavy metal bad guys. So all of these halides are soluble except for silver, mercury, and lead. Fluorides are soluble except for 2A metals. So anything that's in the 2A metals, the alkaline earth metals, are not going to be soluble with fluorides. Nitrates, chlorates, perchlorates, and acetates are all soluble. That's probably your second most important rule. because you're going to run into those a lot. Sulfates are soluble except for the heavy metal bad guys, along with calcium, strontium, and barium. So let's take just a minute and look at a periodic table, because there are some little patterns there that will help you remember some of this. So calcium, strontium, and barium are right here, and silver, mercury, and lead are over here. So silver, mercury, and lead I refer to as those heavy metal bad guys, but the calcium, strontium, barium business going on over here for sulfates is equally important. Then Rule 6 is a little more subtle. Carbonates, phosphates, oxalates, chromates, sulfides, hydroxides, and oxides are generally insoluble, but Rule 1, again, takes priority. So if I put a 1A metal or an ammonium in front of carbonate, oh yeah, it's soluble. So you really want to embrace numbers 1 and numbers 4 early, and then work more diligently on mastering the other rules in this list. So it can be assumed that ionic compounds that dissolve in water are strong electrolytes because they're making those charged and mobile particles we talked about in the last session, and therefore they are very soluble. So using the solubility rules, predict what will happen when the following pairs of solutions are mixed. So KNO3 and BaCl2. Here's your thought process. Ooh, a nitrate. Ooh, a 1A metal. Yeah, that's going to stay soluble. But you also have to, they already told us they're soluble, so that's not a big deal. But if we mix these, then it's like a double replacement reaction. And so back when you were in algebra, you may have learned a method when you were studying factoring called FOIL. Do the first by the first, the outsides, the insides, and then last by the last, if you're going to put together some expressions to make one big giant equation. So if you know that FOIL method, it's the O and the I that are important here. I always think of that when I do the insides first and then the outsides. So I'm going to do the insides, and what would I make? I would make BaNO3. It's a nitrate. It's soluble. I don't have to think any harder about that. And then what else would I make? I would make KCl2, and it's got a 1A metal in it, so soluble. So nothing's going to happen. No visible reaction in VR. These two solutions happen to both be clear and colorless, and so you're going to mix them together, and it's going to be the most boring thing that you've ever mixed in a test tube. Nothing exciting is going to take place. All right, so let's move to the next one. The next one is sodium sulfate and lead nitrate. So if I do the insides, I would make PbSO4. If I do the outsides, I would make NaNO3. That's very soluble, so that's not going to precipitate. But lead you have to think a little harder about. It's a heavy metal bad guy. So it says right up here in Rule 5, sulfates are soluble except for these guys. So indeed, this is going to make a precipitate. So you're going to see a solid form. And for C, if I do the insides, I get FeOH3 because I know nitrate's a -1, hydroxide's a -1. I would need 3 of them, so that's a +3 iron. That's from formula writing. You should be able to do that by now. And then, is that going to be soluble or insoluble? Well, hydroxides are generally insoluble, and iron is definitely not a 1 or 2A metal, so this is going to be a precipitate. So that's going to precipitate. And then what else would I make? I would make KNO3 again. So I would have KNO3, and as soon as I see the K or the nitrate, I can quit thinking about that. This is not going to do anything. So it's just going to keep those ions. So for part B, we made this precipitate. For part C, we made this precipitate. We didn't make any precipitates on part A. So no visible chemical reaction occurs. So we have ways that we describe reactions in solution. The way you are most familiar with is the complete balanced equation. It gives the overall reaction stoichiometry, but not the forms of the reactants and products as they exist in solution. The way this is, like I say, the way we taught you in first year, often also called a molecular equation. Everything's accounted for. Then we have complete ionic equation, which represents anything that does dissolve, hence the need for solubility rules, as ions. And all the reactants and products that are strong electrolytes are represented. And if you make any precipitates, they're no longer ions, you make them into molecules. Then we have the net ionic equations. This is going to be free response, question 4 on the AP exam, and it is something you can practice all year. It is 15 points. It's the fastest 15 points. It's the only 15-point question in the free response. The others are between 8 and 10 points. So you want to get good at this, because this can save your hide and make the difference between a 2 and a 3, or even a 4 and a 5. So what this does is include only those solution components that are undergoing a change. Spectator ions are not included. Spectator ions are like our potassium nitrate that we just did in that last example. That's going to exist as K plus and NO3 minus, which is what they existed as in the beginning. So they don't play this game. They're just a bench warmer. They're sitting on the sidelines, not being able to participate in the chemistry whatsoever. So one thing to consider also is that there is always a conservation of charge in net ionic equations. So not only is there a conservation of matter and a conservation of energy and a conservation of a lot of different things in physics, there is also a conservation of charge law. And so whatever charge you have on the left side of the equation, you must have on the right. And that's going to become really important in the next segment when we do redox equations. Okay, so let me make this a tad smaller. I think that'll work. I think you can see that. And for exercise 9, which you see in a box on your copy, for each of the following reactions, write the molecular equation, the complete ionic equation, and the net ionic equation. So we're going to take aqueous potassium chloride, that is KCl. Now, if you by now have hopefully embraced the patterns on the periodic table, but just in case you're new to this game and you haven't listened to my other files before, I'm going to take just a minute and talk about this. Here's my handy-dandy periodic table, which I'm going to clean up a little bit. You should know by now from first year or from just earlier chapters than this that the 1A's along with hydrogen are all pretty much going to make +1 ions, and when you're doing formula writing, their oxidation state is also going to be a +1. These are going to be +2, these are going to be +3, plus or -4, plus many other possibilities. So what I'm giving you is the most common. Definitely, especially with the nonmetals, they can make lots of different oxidation states, as can these transition metals, which is why we use Roman numerals to tell you which one they're doing, except for silver, cadmium, and zinc, which again, they make a nice little pattern connected right here. The first one is a +1, and the other two are both +2s. Let that pattern sink in. The first one's a +1, the other two are both 2s. All right, so then we go -3, -2, -1. And the noble gases, they don't participate in chemical reactions very often at all, so you don't have to worry too much about them. So most of the time, you're going to have a clue from the chemical formula as to what the oxidation state of your atoms in there are. You also need to know your polyatomic ions. One more reason to know your polyatomic ions. So one of my hints that I always shared with my students was the minute you get that blank periodic table on the AP exam, do this. Do these oxidation states, and also just number one to 8, because that's how many valence electrons they'll have. When we get into bonding, it's really important for you to, at a glance, and instantly know how many valence electrons there are so you can draw valid Lewis structures. But that's another day. So let's go back where we were and focus on this equation. Aqueous potassium chloride. So I know that potassium is K. I know it's a +1 because it's a 1A metal. I know that that's a halogen. It's Cl. I know it's a -1. Added to aqueous silver nitrate. We just talked about the fact that you memorized that silver is always a +1, and you should know your polyatomic ions, which are -1. So that formula is going to be AgNO3. This is how you would have done it in first year. So now you do the insides and the outsides. So the insides are AgCl, because again, everything in this whole situation, because this is an easy example, are +1s and -1s. And then the outsides would be KNO3. And that's where you might have left it in first year. I would hope you learned some solubility rules, or at least used a solubility table or something to realize that this is going to form a solid, which you could also denote with a down arrow, which is my habit. You'll see me do that a lot. But in any event, that's going to be a precipitate. So this is my molecular equation. So check, got the molecular equation done for this first one. Now I need the complete ionic equation, which means I must contemplate for all 4 of these critters, are they soluble or are they insoluble? So I see that 1A metal and I go, yep, that's soluble. Then I see silver nitrate and I take a moment of pause because silver is a heavy metal bad guy. But wait a minute, it's with nitrate. All nitrates are soluble, so indeed this is going to be in solution as ions as well. Must put proper charges. Then I do not ionize that because it's sitting there as a solid. It is not invisible ions floating in solution that could possibly conduct an electric current. If I had a conductivity probe in this situation, as this precipitate forms and you see more and more and more of the solid form, then you will watch the voltage drop and drop and drop and drop because it can no longer conduct as much electric current. Then I see it with double whammy over here with a 1A metal and a nitrate. That is super duper soluble, so off we go. That is my complete ionic equation. Check. Very tedious, not fun, good thought process, not necessary when you get to doing AP net ionic equations, but it is a good thought process, and it is something you should practice until you've totally internalized your solubility rules and can look at this in a different way, which I'll teach you later in a different file when we're doing net ionics. Okay, then the final thing they want is the net ionic equation. What that means is you get to come along and you get to cross out things that are just spectators. And again, I say a spectator didn't participate. It started as an ion, it ended as an ion. Potassium started as an ion as a reactant, it ended as a product ion. Yeah, very boring, nothing at all going on there. The nitrate ion does the same thing. Starts as a reactant as a nitrate ion, ends up as a nitrate ion at the end of the situation. So my net ionic equation is simply the fact that my chloride ion and my silver ion are really the ones that are making the excitement in that test tube, and what they are doing is no longer being invisible floating around in solution. All of a sudden you see this, it happens to be white, this white solid form and float its way down to the bottom of the test tube, and you have a precipitate. So there you have it, all three forms. This one is the one that we're going to work on a lot. And you got to decide, are you willing to write all this mess down and think this through the longhand way, or are you going to practice and practice and practice and get lightning fast at this? Me, personally, I'm kind of lazy. I'd rather think than write. All right, so we're going to do that same drill, but we're going to do it with this equation here. So one more time. Aqueous potassium hydroxide, that means it's floating around in solution, is mixed with aqueous iron 3 nitrate. And that 3 means this is a +3 iron. Thank you for that Roman numeral. It is my friend. To form a precipitate of iron 3 hydroxide, so it stayed iron 3, and aqueous potassium nitrate. Okay, so they're giving me all these clues with this aqueous stuff. Let me amend this to be what an AP problem would be like. Potassium hydroxide is mixed with iron 3 nitrate, period. It would be your job to fill out the rest of this. So let's think about this. Potassium hydroxide. Oh, potassium. Okay, that's a 1A metal. So I know that this is going to be KOH. So because I know that's +1, and I know my hydroxide's a -1 because I have memorized my polyatomic ions. I've already deduced that iron is a +3, nitrate is a -1, again because I know my polyatomic ions. This molecularly would be written as FeNO3 3 times. All right, then what would form? Do insides, outsides. That iron is a +3, so it would need 3 hydroxides. And then I have the outsides, KNO3. Now, of course, you would need to balance this equation. So if I balance this equation, I notice all these 3's are problematic. So I would need 3 of these and 3 of these, and I think I got it. Yeah, so there's a balanced molecular equation. That's the way you did it in first year chemistry. Not all that dazzling. Now you come back and you think about each and every one of these 4 little critters in here, and you figure out, existing as ions or not. So initially, you ask yourself, is KOH soluble? The answer is yes. How do you know? That's right, because it's got potassium, which is a 1A metal. So I write it as K plus and OH minus. Then you go to the next critter and you go, iron, tricky, don't really know a lot about iron. Oh, nitrate, oh yeah, nitrate, that's a good one. All nitrates are soluble. So yeah, Fe3 plus, again, how do I know it's 3 plus? They told me, they told me in code, mind you with the Roman numeral, but they told me. Plus NO3 minus 3 times. All right, then is this iron 3 hydroxide soluble? Hydroxides are generally insoluble. So that's going to be a precipitate, FeOH 3, so I leave it molecular. Hydroxides are insoluble unless they involve something from Rule 1, which are the ammoniums or the 1As. So I didn't make that up. It is a rule. Promise. All right, and then, is this potassium nitrate soluble? Yeah, it's a double whammy soluble. It's got a 1A and a nitrate. It's super soluble. So K plus NO3 minus. All right, it's still not balanced. So what must I do? I must get 3 nitrates on each side and 3 hydroxides on each side. And now I have a balanced, complete ionic equation, best I can tell. Yes, I do. Yes, I do. All right, so then we go net ionic. So what do you see here? Well, forget my little red 3s on there. Just look at the blue stuff. It would let you cross off this and this, not the hydroxide, but definitely the 3 nitrates on each side. Okay, so now these are the real players. The potassiums and the nitrates, they're just spectators. The real players in this game are Fe3 plus those 3 hydroxides to make FeOH3, which is a solid. And there you have it. That's the net ionic equation. Lots and lots and lots and lots of practice with that. So here's all of that all typed out pretty. So now let's actually do some stoichiometry with these, because you knew it was coming, right? The calculator's been sitting there the whole time. You knew sooner or later I was going to pull out that calculator and use it. So it's been at the ready. All right, I'm going to make this a little bigger again. And let's see what we can do with this one. Chemical analysis of mixtures by precipitation reactions. We mix the starting chemicals to form an insoluble salt. We filter the salt out. We dry it to constant mass. Why? Because if we have grams and we know its identity, because we can balance the equation and use our solubility rules to figure out its identity, then we can get its molar mass, and then we can get stoichiometry. So let the stoichiometry begin. We want to calculate the mass. So again, I've been trying to teach you how to mark up your problems so that you can focus very clearly on what it is you're supposed to do. I want the mass of solid NaCl that must be added to 1.50 liters of a 1 molar silver nitrate solution. And by now I hope you're embracing the fact that that's code for moles. Molarity times liters is moles. So they just told us in code the moles of silver nitrate to precipitate all the silver ions in the form of AgCl. So let's think about what's going on here, and let's think about what's going on here net ionically. Let's practice that skill. See that sodium? Yeah, that means this is existing as Na plus and Cl minus when it's added in, and that's going to be added to silver nitrate. All nitrates are soluble, so those are going to exist as ions as well. And there's a heavy metal bad guy in the presence of a halogen, so we're going to make a precipitate of AgCl solid, and then that's my insides. My outsides would be sodium nitrate, and that's still going to be Na plus and NO3 minus. So you either write it or you think it, but that and that and that and that are not in this equation. So I'm going to do this with a net ionic equation for my stoichiometry. So Ag plus NO3 minus yields AgCl minus AgCl solid. And I wrote that a little too far apart. I'll get it right here in a second. Okay, so is this a balanced equation? Yeah, 1 to 1 to 1. And again, I apologize, I do stoichiometry in a table. You are welcome to pause me at this very moment, not get confused by this if you're new to these recordings, and actually watch or actually do your dimensional analysis thing. We'll compare answers when we're done. But if you want to see a different method, then just endure this discussion. This is my mole-to-mole ratio. I need to know the number of moles. And I've been given some amount to get me started, and that was my code for moles right up here. So for my silver nitrate, it's the silver ion that's actually participating here. So I have 1.5 liters of 0.1 molar. Well, 1.5 times 0.1 is going to give me the moles, and that's going to be 0.15 moles. I don't even need a calculator for that. So my amount to get started is 0.15 moles, but again, I got that from saying 1.50 liters times 0.100 mole per liter, which is what molarity equals, cancel, cancel, moles. So I can write it, I can do it in my head, whichever. But if I have 0.015 moles of silver reacting, and that goes with this 1, and this is a 1, that's also 0.15 reacting, and that's coming from my sodium chloride, and that's what they want me to give them, is the mass of the solid sodium chloride. And just for fun, I'm also going to make 0.15 mole of this. So once you figure out what 1 is, you just get to use it all the way across the table to get moles of everybody. And this one's easy because it's 1 to 1 to 1. But if I'd have had a 2, I would have doubled 0.15 and gotten 0.3. If I'd have had a 3, I would have tripled 0.15 and gotten 0.45. So 0.45 if I'd tripled it. All right, so now I know how many moles. Can't I just use the molar mass and come out with the grams? Indeed I can, because if I have 0.15 moles, then I have 0.15 moles times the molar mass, which is in grams per mole, and lo and behold, I'll have grams. So let's get that molar mass. Sodium, because I do have to do this as solid sodium chloride, the source of my chloride ions. So sodium is 22.99. Where'd I get that? Trusty periodic table. I use the College Board one. And then what is my chlorine? 35.45. I have my periodic table handy, and you should too. And when I hit enter, then I get 58.44 grams per mole. And that multiplied by 0.15 equals 8.77. That's 3 sig figs. 3 sig figs. Should have contemplated that in the beginning, huh? But 3 sig figs, 8.77 grams, just like it says right there on the answer. I love it when I get the right answer. So there you go. You probably did something really similar to that in first year when you were learning stoichiometry the first time. The net ionic thing may be a little new. Now, you don't have to do them net ionically. If you want, I'll do this next one molecularly, and you can see that it works out the same way. So when aqueous solutions of Na2SO4, by the way, that's soluble because, that's right, it has a 1A metal, and lead 2 nitrate to be exact, because I know nitrate's a -1, and it took 2 of them, so that lead is a +2. Is that soluble? You betcha, because it's got a nitrate. So everybody's floating in solution at this point. Question is, who's pairing up? So insides, lead sulfate, Pb, 2+, SO4, I know to be a 2-, so that is a correct formula. Outsides, NaNO3, +1, -1, so that's a correct formula, but there would be 2 of them when I balance this equation. So this is 1 to 1 to 1 to 2 in terms of mole to mole ratio. So let's actually read the problem. I'm going to scan the sig figs first this time. I see 3, I see 3, I see 3, I see 3, I see 3 everywhere. So we're going with 3 sig figs when we report this answer. Now, mixed precipitates. Okay, so they told me this. I knew it anyway because of my solubility rules, but I realize you're new at this. I'm cutting you a little slack right now. So calculate the mass of, so that's what I want, mass of lead sulfate formed when? Again, they gave me moles. And again, they gave me moles. They just are doing it in code. Embrace the fact that molarity times liters is moles. So, of the lead nitrate, my amount is 1.25, so my number of moles, clear my calculator over here, is simply 1.25 liters times 0.05. 0.05 times 1.25 equals 0.0625. And which one is that? That's my lead 2 nitrate. 0.0625 moles. Oh, and didn't you know, too, that when you have that and right there, you're in the land of limiting reactant. So you got to get moles of both and then compare and see what's really going to govern how much of the product that you make. So 2 liters times 0.025, 0.025 times 2, I could have done that in my head, sorry, 0.05, 0.0500 to get 3 sig figs moles. Compare, they're both 1s, so it's a fair fight. Who's the little guy? Yeah, who's the little guy? So this is my limit. So I'm not really going to use that. What I'm really going to use is the same amount. It's a 1-to-1 reacting ratio, and I'm going to make, therefore, reacted, RxTD reacted, 0.0500, also, 0.100. How'd that happen? Because that's a 2. So what's 0.05 twice? Don't believe me? See, it's 0.1. All right, so now what am I really looking for? Mass of lead sulfate. Well, I now know how many moles of lead sulfate. It's right there. It's that many moles. So again, moles times molar mass is going to give me the actual number of grams. So I need a molar mass for that stuff. And that stuff is lead sulfate. So let me clear this out and off we go. Lead. Gotta look that one up. That one is 207.2. Heavy dope. That's why I call it heavy metal. Bad guy. It's a heavy sucker. The sulfur's easy. That one's 32.06. And then oxygen is 16, and 4 times 16 is 64. But you can trust me or you can work it out. So I get a molar mass of 303.26. So therefore 0.0500 moles times 303.26 grams per mole equals, so it's sitting there times 0.05, and I get 15.16, but we want 3 sig figs, so I'm rounding that to 15.2. And again, look at that, got the right answer. 15.2 grams of PbSO4. And there you go. So I realize you may do dimensional analysis. That's fine. This is just the way I do it. Doesn't have to be the way you do it. I just found that my kids preferred this method because most of them can do it faster because they wouldn't write all these units down. You know, I'm just trying to be setting a good example here. I got to tell you, if I was a kid writing all this out, I wouldn't be doing all those either because I've already labeled its number of moles over here. I've already labeled its a mole-to-mole ratio over here. I'd have just gone for the mole map, which is the fact that when I have moles, I multiply by molar mass to get to grams and call that a day. Okay, a little bit of a new topic, acid-base reactions. So I'll clear my calculator. Acids, you've already been exposed to, I suspect. They are any compound that, upon reaction with water, produces an ion called a hydronium ion, which is an H plus ion riding piggyback on a water molecule. So H3O plus is correct, H plus is correct. The other piece is going to be the anion, because once you took the H off of the acid, then you have an anion. Then the base is any compound that provides a hydroxide ion and a cation in water. So the Arrhenius definition is that ammonia, NH3, actually, that was the Arrhenius definition, sorry. There is an exception you need to be aware of. Ammonia is an exception because it doesn't have a hydroxide. So Bronsted-Lowry came along with a new theory and said, well, we've got to explain ammonia. So ammonia accepts a proton and makes your good buddy NH4+. That's what you get if you add an H plus onto NH3. Neutralization is when moles acid equals moles base. And by the way, that equals moles salt formed, if you think about it, because acid plus base yields salt and water. So according to stoichiometry, how many moles of acid you made is how many moles of base you made and how many moles of salt that you formed. So each is then neutralized, but I must also tell you that what you're really asking yourself is this salt that's formed soluble in water? But the pH is not always neutral. Just because it's a neutralization reaction, it doesn't mean the pH is neutral, because if your salt is not a neutral salt, then it starts driving the pH of that reaction. So that's a whole other lesson when we talk about salt hydrolysis when we get to the actual acid-base chapter. So stay tuned and make sure you listen to that one too. It doesn't exist yet as of today, but it will. All right, so let's look at this. What volume of HCl is needed to neutralize 25 mils of 0.35 molar NaOH? Okay, they're trying to trick me. Look at that milliliter sneaking in there. You better immediately change that to liters because otherwise you can't get to moles. So 0.025 liters. So get that out of your life and convert it. And now I have liters times molarity, which ding, ding, ding is moles. Oh, I also have a molarity. You know what? I didn't need to go to moles because if I think about this more carefully, they're asking me for a volume, which I'll call V1. They gave me a molarity, which I'll call M1, linked by that fabulous little preposition of. Here's another fabulous little preposition of. So this is V2 linked by that little preposition of to M2, and I have an M1 V1 equals M2 V2 on my hands. Much easier. Okay, so if M1 V1 equals M2 V2, that would be for dilution, but this is actually for acid-base. So AP exam hates it when you do that when you go into acid-base, but this is acceptable. MAVA equals MBVB. Molarity times the volume of my acid equals moles acid. The molarity times the volume of my base equals moles base, and that's what neutralization is about. So I'm trying to neutralize, so this is acceptable. So what am I solving for? Just make that an A, because that's an acid. The H is a big old clue. And that OH is a big old clue that this is a base. Let's make that a B, let's make that a B. So I am solving for VA. So therefore, VA is equal to MBVB over MA equal to plug and chug. 0.350. Volume is 25.0 milliliters. And this is 0.100 molar. Now, I'm getting sloppy with my units here for a reason. The only unit I've got there that isn't going to be canceled is that milliliter. So I didn't have to change it to liters. I can leave it in milliliters. I can report an answer in milliliters, no problem. If I did change it to liters, that's fine too, because I'll just answer in liters, either way. But this molarity and this molarity cancel each other out. So I don't even bother writing them in there and clouding up the view. So VA equals, I turn to my handy-dandy calculator, 0.35 times 25. There's my numerator, divide it by 0.1. And I get 87.5 milliliters. If you don't like that, it's also equal to 0.0875 liters. Both of these have 3 sig figs. Everything had 3 sig figs. 3 sig figs it is. So either one of these is acceptable, whichever way you like to report it. Another chance to practice limiting reaction. I know it's your favorite. I know you're getting good at it too. All right, so let's see what happens here. In a certain experiment, 28 milliliters of 0.25 molar HNO3 and 53 milliliters of 0.320 molar KOH are mixed. Calculate the amount of water formed in the resulting reaction. All right, what is the concentration? That's code for molarity, moles per liter, of H plus or OH minus in excess. Another hint that was limiting reactant if you didn't pick up on this, and when they give you 2 starting amounts after the reaction goes to completion. All right, so this is going to be a stoichiometry limiting reactant mole thing. So really, this isn't my friend. I need to go ahead and change that to 0.028 liters. Is that correct? Did I do that right way? 1, 2, 3. Yep, I did. And this then should become 0.053 liters. Now I'm ready to rock and roll. So I'm looking for a concentration. That's the ultimate. And the amount of water formed. Now, amount is tricky. Amount can mean mole. Amount can mean volume. Amount is kind of ambiguous. AP questions are written a little more carefully. But either way we look at it, we need a balanced equation. So what do I have going on? I have HNO3 plus KOH yields KNO3. Sorry, brain wrote the N first. Plus H2O. Balanced, easy greasy, 1 to 1 to 1 to 1. Nothing really exciting here. So my limiting reactant part is going to be a little bit insulting. So I have 0.25 moles per liter. Multiplied by 0.028 liter. Liters cancel, and I get moles. Go figure. So my number of moles in my little table here is going to be written above this. So 0.25 times 0.028 is going to be 0.007. if I can, well, okay, 0.0065. What did I do? Oh, I hit the wrong thing. That's why. See, sometimes my head is actually better than my calculator. Let's try hitting the right button this time. There we go. Times 0.25. In my head, I was doing a quarter of 0.028, coming out with 0.007. And indeed it is. So 0.007 moles. Again, I wouldn't write that. It's sitting right here as a heading for this table. So what do I got about KOH? Let's do the same thing. For KOH, I have 0.32 for the molarity multiplied by 0.053 liters. And that's moles per liter, so my liters cancel off, and I come out with moles. So that is 0.32 times 0.053, 0.01696. Let's call that 0.017. Who's the little guy? Because it's a 1-to-1 ratio. So somebody's limiting. Who's the little limits? The little limits. So 0.007 is a smaller number than 0.01. So what's the scoop here? That means I'm going to have excess only 0.007 moles reacts. Therefore, if I subtract 0.007 from this larger number, I come out with 0.00996 moles excess. Take a moment, contemplate. OH minus. So I have excess OH minus because this is a soluble thing that's going to be doing this and this. This is soluble. It's going to be doing this and this. Then it's going to make insides potassium nitrate, which is going to do this and this. So these are my spectators. Cross it off, cross it off, cross it off, cross it off. My net ionic equation is the fact that H plus and OH minus make water in a 1-to-1-to-1 ratio. So the fact I have excess OH minus means I have a basic solution, an alkaline solution, a different adjective to describe a basic solution with an excess of OH minus. So if you want me to give you a molarity, which is what concentration is, I got the moles. I just need the liters. Well, there's this thing called total volume. You mixed 0.028 liters with 0.053 liters, add them up, 0.081 liters. So therefore, concentration of OH minus in molarity is what those square brackets are implying, is 0.00996 moles divided by 0.081 liters equals, okay, so I'm on the new operating system. If you've not upgraded, and you can because you have an 84, you should, because you're going to like this. I'm going to go right on up here, and I'm going to grab the moles, and I'm going to divide it by, I'm going to grab the liters, and I didn't do any extra typing. And I get 0.1229, which to 3 sig figs, which is the sig fig flavor of this problem, I get 0.123 molar OH minus. Now, I can either write this as OH minus bracket and not put this, or I probably could have erased this faster, sorry. Oh, needs that minus sign though. Or I can write it that way. So this is this, doing these brackets is the same thing as saying molarity, and I could have just said 0.123. Okay, we're making progress. Let's talk about titrations. With titrations, we're doing what's called a volumetric analysis. So anytime you read a problem and it talks about a volumetric analysis was performed, you need to think, aha, a titration, a burette, a long skinny tube with a little valve at the bottom called a stopcock, which I know is a funny name. And when you open that little stopcock, it goes drippy, drippy, drippy down into something else. But the point of the burette is you pay a lot of money for them. They're about 50 bucks. Don't break them. And you get very, very, very accurate volumetric measurements. So it is a technique for determining the amount of a certain substance by doing what we call a titration. There are 2 players in a titration, the titrant and the analyte. The titrant is the substance that is delivered from the burette going drippy, drippy, drippy. And that way you know its volume very accurately. The analyte is the thing you are analyzing, and hence the name. And it is either you know its mass or you know its volume very, very accurately, so that you know the number of moles. So the goal of knowing these accurately is to get to the number of moles. So stoichiometry is in your future because, we're going to get some mole-to-mole ratio things going on when we actually do the math, do the stoichiometry to analyze our results. So some new vocabulary words, unless you did some titrations in first-year chemistry, are equivalence point. That's when something is equivalent. And what is it that is equivalent? The moles of acid and the moles of base. So the moles of OH minus are equal or equivalent to the number of moles of hydronium ion. The indicator undergoes a color change at the end point. And standardization is this procedure that we're doing where we establish the exact concentration of a reagent. So we often, instead of reporting something to 0.010 molar, we can report it to like 0.0113 molar or something to that effect. We get a lot more significant digits at the end of that. It's not just a guess. So it's a really big deal in industry and analytical chemistry and CSI and drug labs. And I don't mean the illicit type of drug lab. I mean labs that are actually manufacturing useful pharmaceuticals. So let's look at this one. It's a lot of words to read here, isn't it? It's a long problem. Okay, a student carries out an experiment to standardize, which means determine the exact concentration of a sodium hydroxide solution. Okay, NaOH is involved. And it's soluble because of that sodium there. To do this, the student weighs out a 1.300 gram sample of potassium hydrogen phthalate. That's a pH like phone, so phthalate. And it's a silent pH, by the way. KHC8H4O4. I feel a massive molecular mass coming on in your future, which we often abbreviate as KHP because potassium hydrogen phthalate is a mouthful. The molar mass of this substance, thank God, they told me what it was, is 204.22 grams per mole, has one acidic hydrogen, so this one hydrogen, that's why it's written over here as a loner, instead of written over here in its organic clump of C's, H's, and O's. That's the H that's going to come off. So the student dissolves KHP in distilled water, adds phenolphthalein, which is that indicator you may have used in first year that is colorless in acidic solutions and pink in basic solutions. And it's a really fun word to say, phenolphthalein, and titrates the resulting solution with the sodium hydroxide. So our two players are KHP, which is this big hairy formula right there, and sodium hydroxide to the phenolphthalein endpoint, which means color change. And if the experimental designer did their homework, they chose phenolphthalein because that color change is going to occur at the same place as the actual equivalence point where moles acid equals moles base. Those E words can get a little confusing. Endpoint, color change. Equivalence point, actual moment when the math is correct, where we have exactly the same number of moles of acid and base. So the difference between the final and initial burette readings indicates that 41.2 milliliters of the sodium hydroxide was required to react exactly with this number of grams of KHP, which means I can get to moles of KHP, and you gave me a volume, so I bet you want me to calculate molarity, and indeed they do. Calculate the concentration of the sodium hydroxide solution. Whew. You may need a beverage after that. That was a lot to read. Okay, so let's just kind of dissect this puppy. Moles of KHP is equal to moles of NaOH at equivalence point. That's an EQ point. Okay, easy enough. Moles of KHP we can figure out really quickly because they gave us the mass and they gave us the molar mass, and there isn't anything easier than that. 1.300 grams divided by 204.22 grams per mole gives me moles. 1.3 divided by 204.22, and you may do dimensional analysis to make that happen. I just do it in mole map, which mass divided by molar mass gets you moles. So 0.00637 is what I'm going to write down. How many sig figs? 5, 5, 5, 4. 4 sig figs. So phooey. 6365 becomes a 6. One more time. 636. That 5 becomes a 6. Yes. I'm actually just going to leave it in my calculator. Moles of KHP. So, molarity is your friend. This is going to equal the same number of moles of NaOH. And molarity is what we are seeking. You got to embrace the fact that concentration is molarity in moles per liter. If you know moles, can't you divide by liters and get to molarity? You betcha. So molarity equals moles per liter for NaOH equals 0.006366 yada yada moles of NaOH. Again, because of that one ionizable hydrogen, one hydroxide. So this is a 1-to-1-to-1 ratio. If they'd have given me an acid that had 2 H's or a base that had 2 hydroxides, I got to double something or have something. Common sense is your friend. All right, so now I have my moles and I need my liters. They gave it to me in milliliters, but that's okay. I can make that conversion. 1, 2, 3 places, liters. So what's sitting in my calculator divided by 0.0412 equals 0.1546 to 4 significant figures. 0.154, I get 5. If I leave it exact. This happens sometimes. Depends on how you rounded, where you rounded throughout the problem. If you leave it all in the calculator, then I get 5.5. They have 4.6. Close enough. It'll get you the answer either way. And that's a molarity. And it is of the NaOH solution. Just to finish it off nice and pretty. And there you have it. All right, let's see what else we have in store for us. This is my last one. We're going to stop. If you can hang with me this last one, then we're good. And by the way, these problems are way too wordy. AP problems are not quite as bad. An environmental chemist analyzed the effluent, that's how you say that, not affluent like you're rich, but effluent, which is a released waste material, yummy, from an industrial process known to produce the compounds carbon tetrachloride, very big carcinogen, causes cancer, and benzoic acid, not so scary, a weak acid that has, again, with the one acidic hydrogen. They're taking pity on my soul here and trying to make this a simple NaOH kind of titration and not complicate anything by having to double something or have something. We'll get to that with AP problems. A sample of this effluent weighing, you're going to give me a mass then, weighing this many grams was shaken with water. The resulting aqueous solution required this many milliliters of this much NaOH for neutralization. Calculate the mass percent of this in the original sample. Okay, so mass percent is part over whole times 100. If I can get to grams of this stuff, I can take this number of grams over the grams of the effluent multiplied by 100, Jeff Foxworthy, 5th grader math, and I'm done. So the tricky bit is understanding that we have a real kind of a titration situation going on here. So to get started with this, let's figure out the moles of something, anything. So let's go with the moles of the NaOH. So the moles of NaOH is equal to molarity times liters. 0.1546 moles per liter times 0.01059 liters. Where'd I get that? That's right. I moved the decimal 3 places from milliliters to liters in the proper direction. And so when you multiply that out, let's see what you get. 0.1546 times 0.0159. I left the 0 out. 1059. That would be bad. And I get 0.0016, yada yada. How many sig figs? 4 it is. 4 sig figs in this problem. So, what am I going to write down? 0.00. Nothing significant yet. Now I get to a significant digit. 1, 6, 3. Think about the 7. Leave it a 7. Moles of NaOH. Therefore, that's how many moles So this times its molar mass. Did they give it to me? No. Oh, good grief, Gertrude. It's a big molar mass. So off we go. Where is it? Where's this little formula even? I lost it. It's here somewhere. There it is. There it is, right there. All right, so what do we have? We have 6 H's. Do you see them? 1 in front, 5 hidden within. So that's 6 times 1.01. That's 6.06. Plus 7 carbons. 7 times 12.01. Plus 2 oxygens. That's 32. 16 apiece. I come out with 122.13. So that times, go back up and grab this. Love this feature. Equals 0.19995. Okay, 0.19995. I know I went 1 sig fig too far, but good grief. Of grams of benzoic acid. Oh, that should have been benzoic acid because these moles are equal. This mole of, oh, I wrote KHP. I should have written benzoic acid. That's where I screwed up. So I had the last problem stuck in my head. Okay, so now that I know grams, mass percent is very simple. And it is the 0.19995 that's sitting in my calculator. I could have written the chemical formula, I just did it in words. And the 0.3518 gram sample times 100 to make it a percent equals times 0.3518 times 100. 7.03. Something is terribly wrong. I multiplied instead of divided. I'm a doofus. All right, let's try this again. I'm going to grab this. Divided by, hit the right button this time, McCormick. Divided by 3.3518. Enter, times 100. And if you use the right operation, you get the right answer. Go figure. So 56.84 would give me 4 sig figs. And that's a percent of the benzoic acid, HC7H5O2. And there you have it. Okay, so just a little bit of a foreshadowing. We're going to go into oxidation reduction. It'll be a much shorter recording. You have seen the dark side of this chapter. Also, I remind you that I will soon embark upon making different segments of the net ionic reaction explanations AP style. So just humor me and please memorize your solubility rules. And I'm certain you've already mastered your polyatomic ions, but if you haven't, then hang your head in shame. What you waiting for? Also memorize your polyatomic ions. Talk to you again later. Bye.